Hi and welcome to the lesson of real analysis. And in this class, we are going to talk about the bounds of a set. So we will talk about bounded and unbounded sets. We will see the definition and then we will take some examples to make it more clear that what actually are bounded sets and what are their bounds. So let's talk about bounded above. So there are two bounds actually. There is bounded above and bounded below. So set bounded above, the definition is let S be a subset of real numbers. Say R, we say that thus uh we say that S is bounded above if there exist. So this symbol is for there exist a real number, or if there exists, we can say that if there exists a number B belongs to R, and it's not necessarily not necessarily it is not necessary that the upper bound is from the set, so necessarily not necessarily a member of S, so the number B is not necessarily a member of set S, such that symbol for such that X belongs to S implies X is less than equals to B for all X belongs to set S. So what does it mean actually is that if we have a set of numbers, for instance, let's talk about this interval that is 1, 3. If we have an interval and we can see that the elements of this set are between all the numbers between 1 and 3. So all the real numbers, we can write all the numbers between 1 and 3, and the set belongs to real numbers. So it's a subset of real number. It belongs to real numbers and the set contains all the elements between 1 and 3. So it says that if there exists a number B, and if we have a number B such that it belongs to R, B belongs to R, and it's not necessary that this number B should be the element of this set. It is not necessary. So not necessarily a member of S, such that X belongs to S implies X is less than equals to B for all X belongs to S. It means that for each member of this set, that is between 1 and 2, all numbers, there exists a number B which is greater than all these numbers, that are contained in the set. So that's called the upper bound of the set. So the number B is called the upper bound. So we can see here that in this set, for instance, if we talk about this set, so this 3 here is not included in the set. And one thing here is that it's less than or equals to, right? Less than or equals to. So the biggest element of the set is also the upper bound, and we will see in the later studies that it is actually the least upper bound of the set. So x is less than or equal to number b. So for instance, if we talk about this set 1, 3, so it contains all the numbers between 1 and 3, excluding 1 and 3. So 1 is excluded, 3 is excluded. So it's an open interval. And we can see that the biggest number in this set is less than 3, right? Because this 3 is not included in the set. So this 3 is the upper bound of the set. So it's the element that is largest of all the elements in the set. And uh, also 4, 5, 6, all these numbers, and every number we can write here, every number that, let's say a greater than equal to 3 is the upper bound of this set, because all these numbers are greater. So 3.1, 3.2, 3.3, like that, 3.001. Every number is the upper bound of this set, 3 and bigger than 3. So these all numbers are called the upper bounds of the set. So that's what the definition is telling here. And if there exists no real number b satisfying this condition that is mentioned in the definition here, if there exists no b, so the set is said to be not bounded above. So we cannot say that the set is bounded above, because we cannot find any upper bound if no such element b exists that is largest of all elements. Okay, so we will see some examples in the later stages. Okay, now let's talk about set bounded below. So similarly, the definition is more or less same. Let S be a subset of R that is real numbers. We say S is bounded below if there exists a real number, let's say A, such that, and it is also not necessarily this element should be the member of the set S, sorry. There exists A, not necessarily the member, not necessarily a member of S, member of S such that X belongs to S implies X is greater than equals to A for all X belongs to S. So there should be a number A, which is less than or equal to all the less than all the members of A. Okay, so sorry, all the members of X. So let's talk about this interval 1, 3 again. So this 3 was the upper bound of the set, because we have the element 3 that is largest of all the elements of the set. And if you look at this 1 here, so we can say that this 1 is the lower bound, because this is the smallest of all the elements of the set. So every element in the set is larger than 1. So this is the condition that X is greater than or equal to A. So which means that X is greater than 1, and it can be it can also be equal if this set was closed like this. Then we also, let's talk about this closed set. For instance, if this set was closed and if 1 is included in the set, then again this 1 is either less than all the elements or it's the least element of the set. So this 1 is lower bound in this case. So this is the lower bound of the set. And then we have the definitions for least upper bound, which we call supremum. So least upper bound, that is the supremum, SUP, supremum. And one more thing to note here is that uh, note is that the set bounded above has an infinite number of upper bounds. So the set bounded above has infinite upper bounds, and same with bounded below. Bounded below has infinite number of lower bounds, as we see in this case that every number less than equals to 1 is the lower bound of this set. For instance, 0, -1, -2, and all the numbers, and that's, you can say 0.999, 0.98, 0.56, all the numbers less than equal to 6 are the lower bounds for this set, and all the numbers greater than 3 and greater than 3 are sorry, all the numbers that are greater than 3, and 3 itself is the upper bound of this set. So infinite upper bounds and lower bounds for the bounded sets. And the least upper bound, that is supremum, we say that it is if the set of all upper bound of set S of a real number has the smallest member k, then k is said to be the least upper bound. So in this case, 1, 3, the is okay, so we say that these all numbers greater than 3, we said that b greater than equal to 3, so all numbers greater than equal to 3 are upper bounds of this set. Okay, upper bounds of this set. But what actually is this set, that is b greater than equal to 3? So every number 3.0001, like 3.75, 3.947, 10, every number that is greater than or equal to 3 is the upper bound. And then the smallest of these upper bounds, the smallest number of these upper bounds is called the least upper bound. So in this case, the smallest number of these upper bounds is, we can see it is 3. Every other number is bigger than 3. So the least upper bound of the set is 3. And similarly, for the greatest lower bound, it is the greatest of all the lower bounds. So this is greatest number of all the lower bounds. So if we see in this set, so every element that is lesser than 1, and 1 itself is the lower bound of this set, but what will be the largest element of all the lower bounds? So it will be 1, because every other number is less than 1. So the largest element, that's why we called it as greatest lower bound. So it is the greatest number of all the lower bounds. So these are the definitions of lower and upper bounds. Now we'll take some examples to understand this thing. So let's talk about the natural numbers. So the set of natural numbers, we know that it is start from 1, 2, 3, 4, and so on. So in this set, if we look at this set, we can find a least element of the set, that is 1. Least element of the set is 1. So this is the lower bound of the set. And in fact, this is the this is the lower bound. Okay, so lower bound equals to 1. Lower bound of the set is equals to 1, and we can see that the least number is also 1, but it is the no number is lesser than this number in the set. So it's the least lower bound of the set, and we can also call it the greatest lower bound because no other number is greater than this number in the lower bounds. So this is the greatest of all in the lower bound. So this is the greatest lower bound. So greatest lower bound of this set is 1. And so it's bounded below. We call it bounded below because this set has a lower bound. So it's bounded below. But in the upper bound, if we see, this is going to infinity and we don't know what is the upper bound. So this set has no upper bound. So no upper bound. So if it has no upper bound, then it has no least upper bound. Therefore, this is not bounded above. So this set is only bounded below. So the set of natural number is bounded below. And then we have the sets of rational numbers. And similar is the case with rational numbers, but in rational numbers, there is no bound. These are not bound, neither bounded above nor bounded below. Above, not bounded below. So these are not bounded above, not bounded below. And similarly, the set of integer, not bounded above, not bounded below. So we cannot find the upper and lower bounds for these sets, so we call it unbounded sets. So these are unbounded sets. These are the examples of unbounded sets. And then every interval, open interval a, b, semi-open interval a, b, or like this, sorry, or this is closed interval, this is semi-open, semi-open, and open interval. All these intervals are bounded and the bounds are a and b. So for every set, for each set here, the lower bound is a, and we can call it greatest lower bound, and this is least upper bound. So every open, closed, or semi-open interval has its greatest lower and least upper bound. That is actually the numbers that are the corner points, that are the end points, or the points, end points, whether included or not included. So they are the least upper and greatest lower bounds of the set. So these kinds of sets, and we can actually take some other kind of sets. For instance, we can check whether this set 1 over n such that n belongs to the natural numbers. We can check whether this is bounded or not. So on number line, if we check this set, what kind of numbers we have? So first of all, it's 1 over 1, then 1 over 2, then 1 over 3, 1 over 4, and dot dot dot. So on the real line, we have, if we have 1 here, for instance, then 1 over 2, 1 over 3, 1 over 4, 1 over 5, it's going back, and eventually it will, the limit will reach to 0 here, 0, right? So this this set is bounded because we can see that we have the lower bound that is 0 and the upper bound that is 1, because the maximum element of this set is 1 and the least element is 0. It's outside the set, it's not in the set, because 1 over n reaches to 0 when n reaches to infinity. So we are not talking about infinity here, so this 0 is not included in the set, therefore this is outside the set, but it still is, it is the least greatest lower bound. It is the lower bound of the set. So we can say that this set 1 over n is between 0 and 1. So the least upper bound of the set equals 1, and greatest lower bound of the set equals 0, where 0 does not belongs to the set. And we already mentioned earlier that not necessary that the least upper bound or greatest lower bound is from the set. Let's take the second example. For instance, -1 to the power n times 1 over n such that n belongs to natural numbers. Again, if we see the set and if we construct this set on the real line, first of all, we can write it as -1 half, -1 over 3, 1 over 4, -1 over 5, and so on. And eventually, we can see here that the largest value in this set is going to be 1 over half, because no other value can attain larger than 1 over half. So 1 over half is the largest value, and the smallest of them is -1, because every other number is going to be the greater than -1. For instance, if we have -1 over 3, it's greater than -1. -1 over 5 is greater than -1. So the least number we have is -1, and the largest is half because it is greater than every number, because it's 1 upon 4, and then again we are going to get 1 over 6 here, and so on. So this set is bounded between these two numbers. So we can say that, and these bounds are included in the set. These bounds are from the set. So the least upper bound or infimum, supremum. Least upper bound is the supremum. So the supremum of the set is 1 over 2, and the infimum of this set is -1. Similarly, if we take an example, let's say 1 plus -1 times to the power n times 1 over n, such that n belongs to the natural numbers. Again, we can construct this set. So clearly this set equals 0 when n is 1, then 3 over 2, then 2 over 3, then 5 over 4, then 4 over 5, then 7 over 6, then 6 over 7, and so on. So we can write this set. So we can rewrite this set in this manner, that is 0 over 1, 2 over 3, 4 over 5, and then continue, and then union 3 over 2, 5 over 4, 7 over 6, dot dot dot. If we look at this set here, so we can see that the numbers 2 over 3, 4 over 5, so it's increasing in the manner that it will reach 1, right? 4 over 5, and then we have 6 over 7, like that. So it's reaching 1. And on the other hand, this set is also tending to 1, as it's 3 over 2, 5 over 4. So it's decreasing. Actually, it's decreasing in this order, 7 over 6, and then decreasing, and it's reaching 1, tending to 1. So therefore, if you look at this set, the largest number of this largest number can be 1, but not from the set, does not belong to the set, or not actually the largest number, but we can see that this tends to 1 from here. And now from this set, this number 3 over 2 is the largest number, because 5 over 4 is lesser than 3 over 2, 7 over 6 is lesser than 3 over 2, and so on. So the largest number from both of these set will be 3 over 2, because all these numbers here are less than 1, but these numbers are all greater than 1. But as it is approaching forward, it is tending towards 1. So this 3 over 2 belongs to the set S. So we can say that 3 over 2 is the least upper bound because it is the largest number, and 1 is the greatest lower bound. So the set is bounded between 1, which is not in the set. 1 is not in the set, but this is in the set. So in this way, we can write the infimum and supremum of the sets. And then we have one more example. Let's consider this example. 4n plus 3 over n such that n belongs to naturals. So the elements of this set will look like 7, 5 whole 1 over 2, 5, 4 whole 3 over 5, and then 4 whole 3 over 5. Sorry, 4 whole 3 over 4, 4 whole 3 over 5, 4 whole 3 over 6, and so on. So if we look at this set, and we can just write it is in this way: 4 plus 3 over n, okay, such that n belongs to n. So if you look at this 3 over n, so the largest possibility we can write in this manner: 4 plus 3 over 1, 3 over 2, 3 over 3, and so on. So the largest possibility is that the biggest number can be 3 in this set. So 4 plus 3 is going to give 7. So the largest element from the set can be 7, and the smallest element of the set can be this 3 over 3. Then we have 3 over 4. So the smallest, we are looking for the smallest element in the set, and this is approaching to 0 as this set, only this set is approaching to 0 when n is tending to infinity, because 3 over infinity is 0. So this is approaching towards 0. So the least element can be 0, but not from the set, very near to 0. So we can say that the least element is 4 plus 0 equals to 4. So the set is bounded between 4 and 7, where 4 does not belongs to the set and 7 belongs to the set. So the least upper bound of this set is 7, and greatest lower bound of the set is 4. Now let's move to the next example. Let's say that we have a set question is the set equals sine pi over 6, comma sine 2 pi over 6, comma sine 3 pi over 6, comma sine 4 pi over 6, and so on. Now for this set, this is a tricky one, but it's easier if you know that the function sine x is always bounded between 1 and -1, because the maximum value that sine x can attain is 1, and the least value that sine x can attain is -1. So the set is bounded between 1 and -1, and somewhere we are going to get 1 and -1. So sine pi over 2 equals 1, and then we have sine 3 pi over 2 equals -1, right? So somewhere here in the set, we are going to get sine pi by 2. For instance, here 3 ones are 3, 3 2 6. So sine pi by 2 it's 1. So we are going to get the greatest number 1. And somewhere we are going to get sine 3 pi over 2. For instance, when we are going to have sine 12 pi, oh sorry, it's 6, so 6, and let's see which number should come for this negative. So we have sine 9 pi over 6 somewhere here, so we will have 3 sine 3 pi over 2, and we will get -1, and it cannot go below than lesser than -1, because sine is bounded between 1 and -1, and it also belongs to the set both 1 and -1. So this set is bounded, and the supremum of this set, or greatest lower least upper bound, is 1, and infimum or greatest lower bound is -1 for this set. So these were some examples we discussed, and one more last example that I want to discuss here is that let we have the set S equals -1 to the power n times 1 over 4 minus 4 over n, and this set n belongs to the natural numbers. This, now we can construct this set, so we can easily construct this set on the real line. So let's construct the set on the real line first. So we can construct this set on the real line by taking some n is equals to 1, 2, 3, 4, and so on. So for n equals to 1, we get this number, 15 over 4. For n equals to 2, this. For n equals to 3, this. For n is equals to 4, this, and so on. We can construct the set, but we can see that no number greater than 15 upon 4 we can get in this set. So clearly the supremum of this set is 15 over 4, and no number lesser than -7 over 4 we can get in this set. So the infimum will be 7 over 4, because it's the least element we can get in the set. So it's greatest lower bound, and this is the least upper bound, because this is the maximum of the all elements from the set. And so in this way we can compute the least upper bounds and greatest lower bounds of the sets. So hope you guys learn from this lesson, and we'll come up with some more topics in the next lesson. That's all for the time being. Thanks for watching the lesson.